Hello and welcome to this presentation on node sampling by partitioning on graphs via convex optimization. This is work carried out by Christian Rusu and John Thompson at the University of Edinburgh as part of the University Defence Research Collaboration. So in this setup, we consider a network of multiple sensors, and these are measuring an environmental parameter such as temperature and sending their data to a central node. We consider that the sensors are low size, weight and power, and so therefore they cannot continuously measure for long periods of time. So here's an example of a small sensor network of 10 sensors, and the sensors are shown in blue, and the lines between them show the connectivity or the relationship between those sensors. And in our problem, we may wish to estimate, for example, 7 parameters from the environment, and in a simple evaluation we would select 3 out of the 10 sensors to perform that estimation, and these represent the optimal sensors in order to give us the best result for our problem. Now the only problem with that approach is that 3 sensors are activated all of the time and 7 sensors are never used. So the batteries on 3 of the sensors will run out too quickly, and we're left with 7 sensors which are essentially useless. And so our objective is to balance the activation of all of the sensors so that all 10 sensors are used equally, and therefore their batteries will drain at roughly the same rates and will achieve the maximum lifetime of the network. So in our solution, we found through analysis that selecting more sensors always helps to improve performance, but critical are the properties of the so-called network fast Fourier transform matrix, as these show the connectivity between the different sensor types. So in this example we have 100 nodes and we split them into 3 partitions, and these are shown by the blue, green and red colour. So each colour will be activated at a different time to measure the system. Here's a second example for the Minnesota road network. This time we have 2,600 nodes, but again we split them into 3 groups, and again these are shown in blue, green and red. For this Minnesota road network, we have evaluated the trade-off between the energy consumption of the nodes and the mean squared error, or the accuracy, and we find that if we want a low mean squared error or high accuracy, unfortunately the energy consumption increases rapidly. But if we can tolerate a higher mean squared error, then we can reduce the energy consumption of the network very significantly. So overall we have a trade-off between the mean squared error and the energy consumption. So in conclusion, networks can be scheduled to operate in a time-efficient manner, and the key concept or the key advance in this work is that of band-limited graph signals that show the connection between different nodes in the network.